I'm Anil Kumar. Welcome to my series on calculus. This is the third lesson on introduction of calculus. We'll look into details of rate of change or gradient. Our focus will be to visualize and understand the concept. We'll cover the topics mentioned here. The basic idea is to improve the communication skills while answering the questions for this particular video. We'll visualize to remember and recall. We'll estimate gradient or slope of any point on the curve. We'll relate gradient and concavity. We'll identify critical points. We'll find the conditions for extrema, means maximum or minimum value, sketch graph of the gradient, and sketch graph of a function. So let's begin with estimating the gradient. So here is question number one. The session is going to be very interactive. I'd like you to pause the video, copy the question, answer. The hints are also provided for you. Question number one is estimate gradient of the function f of x equals to 2x cubed minus 3x plus 4 at x equals to 1. Now I have provided the graph of the function of this cubic function in green to help you find the solution. So from the graph, you have to estimate the gradient of this function at x equals to 1. Perfect. Question number 1b. Calculate gradient of the function f of x equals to 2x cubed minus 3x plus 4 at x equals to 1. Now in this particular case, you have to calculate using the difference quotient formula which we learned earlier, right? So at 1, it will be limit h approaches 0, f of 1 plus h minus f of 1. So you can calculate these values since the equation is given to you. Now once you calculate, you can check how close are you to your estimate. Question number 1c is explain a method to find another point on the graph with the same gradient. Correct? Now the method is shown here on the graph. I'd like you to pause and understand what could be the method to find another point on the graph with the same gradient. Now let's look into the very first question, which is estimate the gradient of this function at x equals to 1. So at x equals to 1, we have shown a line here. That's the point at which we want to find the gradient. So you'll draw a tangent line. So the step here is to draw a tangent line. At x equals to 1. So that is what is done here. This is the tangent line at x equals to 1. And now we can make a triangle to find out the gradient. So now select 2 points on this line, make this triangle, which is right there. And what is the gradient? Gradient g, or you can say slope m, is equal to change in y over change in x, correct? So in this particular case, the change is y is from this point is 6, right? So that point is at 6 and this is 0. So the change in y is this particular distance, which is 6, correct? So change in y is 6 and the horizontal distance is from 0 to 2. Change in x is 2, right? So this distance is 2. So when you divide 6 by 2, you get your answer as 3. And therefore, the solution for 1a is 3, correct? So that is how you have to find from the particular graph. Now, you can always use the difference quotient formula, and when you substitute the value of 1 here, these values will be 1, and then 1 plus h, expand and simplify, you'll find the same answer, which will be equal to 3. Correct? So you see that both the solutions are fairly accurate in this particular case, since we had the solution which was a whole number, right? But normally it will not be the same. Estimate, there could be some error. Now part C is to draw parallel line tangent to the curve in that case, you can actually find another point on the graph with the same gradient. Same gradient means same slope, right? So same gradient or same slope. So that is possible only when you have parallel lines. So here we have drawn a line which is parallel to the given line, and we can find the point on the graph where it is again tangent to the graph, and we find that this point is at -1. So at x equals to -1, we have same slope as at x equals to 1. So that is how you could do such questions. So I hope you've understood the method of calculating the gradient and also finding another point on the graph where we could have the same gradient, right? Let's take the next question now, which is question number 2. As you understand that gradient g at a point is the slope of the tangent line at that point on the graph. So based on this, we have question number 2, which says identify interval or points where, now it has 5 parts, where gradient is positive, gradient is negative, gradient is 0, gradient is decreasing, gradient is increasing, right? So increasing and decreasing. So we have given a very interesting graph here. We are going to use this graph many times. There are points identified as A, B, C, D, E, and F on this particular D, E, F, and G on this particular graph. Now you need to mention where the gradient is positive, right? So pause the video, answer this particular question, and then look into my suggestions. Part A, the gradient is positive means we have slope is positive. So if I draw a tangent line, for example, if I draw a tangent at A, we see it is rising. So when the slope is positive, that means the tangent is rising, or you can say moving upwards, right? So its tangent is in this particular direction. Is that clear to you? So if you draw a tangent, you'll find that from A to C, the graph is definitely rising, right? So looking into imagining this goes up to the infinity, so we can say the graph is rising if the value of between A to C, we can say, right? So it is positive between A to C. So that portion it is rising, and also it is rising from E to G and thereafter, right? So E to G also it is rising. Now where is the gradient? Negative. The graph is decreasing, the gradient is decreasing between C to E. So that will be our answer for gradient being negative. Now where is the gradient? 0. Gradient is 0 at the turning points. So we have to look for turning points which are C and E, correct? So if you draw a tangent at the turning point, the slope will be 0 since those will be the horizontal line. So here we have the point C and point E. Now C happens to be the local maximum and also the absolute maximum value for this particular function. And E is going to be absolute minimum value of this particular function. So you can say E is also a minimum point and C is a maximum. It is important to note that at maximum and minimum, what is happening? The gradient value g is 0, right? So at both these points, g equals to 0. Now another interesting thing which we have discovered here is that the gradient at, we'll use a different ink to explain the concept, the gradient at C is from increasing to decreasing, right? So that is how it is changing at maximum. Whereas in case of minimum, the gradient is from decreasing to increasing. So that gives you the minimum value. So it's a very important visual display of how do we identify maximum or minimum from a given graph. Now, D is gradient is increasing. Now, gradient is increasing does not really mean that it is positive. the gradient could be negative and still increasing, correct? Now, how do we figure out the portion where the gradient is increasing? Well, from A to B, we see it is positive and the slope is increasing steadily. However, at C, the slope is not positive high value, but it is zero. So what we notice here is that the gradient is increasing from A to B, right? And then from B to C, it decreases. So the next part is gradient is decreasing. So as we move along, we see B to C, it is decreasing. Why? Because we know at A, it is almost zero and at C it is almost zero. So definitely there's a turning point in gradient between these 2 points, and that is at B. Now B is a very interesting point. We also call this point B as point of inflection. So what we note at B is that the gradient changes from increasing to decreasing. So we say G changes from increasing to decreasing. Perfect. Now, as we move forward, we see that from C to D, it is decreasing. From 0, it is becoming more and more negative. So in this portion of the graph, we see that G is less than 0, right? At, at this point, however, G is minimum since it is most negative. So at this point, we see that it is most negative. And here it is 0. That means the gradient must increase from D to E, right? So gradient is increasing from D to E, but is decreasing from C to D. You get the idea. So again, at D also, we have a point of inflection. So in short, we write this as POI, point of inflection. Well, in this particular case, the gradient G is changing from decreasing to increasing. So what we infer here is that whenever there is a change in gradient, we might get a point of inflection as we have seen in this particular graph. Perfect. Another part of very important part of this graph is the concavity, which I would like you to work on. This portion A to B is concave up, right? So do you see this particular portion? We can say this particular portion is concave up. And the portion from B to D is concave down. So this particular portion, we can say from F to G also, this portion is concave down. Can you correlate this concave up and concave down with increasing or decreasing behavior of the gradient? So observe and write down your observation. So let's move forward to the next question now. Question number 3. Graph of the function f of x is given below. Identify the intervals where, so this time we will relate the function value with the gradient. The very first one is where the function f of x is positive and the gradient is negative. Now f of x is positive if the graph is above the x-axis, right? So f of x is positive in this particular portion. Now within this portion, where do you find that the gradient is negative? So when we say that f of x is positive, it means we are looking into this particular portion. Is that clear? So it is positive here. Now the second part to this is where the gradient is negative. Now where is the gradient negative? Gradient negative means that if you draw a tangent, it will be coming downwards. So what you find here is that from C to D, it is negative, correct? Slope of the tangent is negative. So that is how we see both the conditions are being met along the path C to D. So we can write down this answer as C to D. Is that clear to you? Perfect. Likewise, you look into the other conditions. Now we are saying that f of x is negative and gradient is positive. So that means we have to look into the other half where f of x is negative. So let me just change the color and then we'll highlight it and then help to find the solution. So we are saying now f of x is negative. So which portion on this graph is the one where f of x is negative? So it is this portion where f of x is negative. Clear? Amongst this portion, where is the gradient positive? So let's try to highlight the portion where the gradient is positive. So gradient is positive when the graph is increasing, and what we have seen is from F to G. So this particular portion, the gradient is positive. So we can say from F to G, the function is negative, but the gradient is positive. So if you draw a tangent on a graph in this particular area, it will be rising and positive. Perfect. C. Gradient is positive and increasing. Now we're only talking about gradient, which is positive and increasing. So what we noticed earlier is that it goes from 0 to positive value and then it goes from a positive value to 0. So gradient is definitely positive and increasing between A to B. So that will be the answer. So not the whole segment A to C, because from B to C it is positive but it is decreasing. So that goes into part D. So it's a very interesting exercise. I like you to really focus and then answer these questions. Now E is gradient is negative and increasing. Gradient negative means we are going to look into the portion from C to E. Now in this portion, C to E, where do you find that the gradient is increasing? So negative and increasing. It is maximum negative at D and then it goes to 0. That means it must be increasing between D to E, right? So this point is E for us and that is our answer, D to E. Next, gradient is negative and decreasing. So it is negative and decreasing definitely between C to D. Perfect. So that is how we can actually find the solution. Now from this particular graph, you can also notice a couple of things. Let me write down here. When we are talking about the concavity and when we say when the graph is concave up, the graph is concave up whenever the gradient is positive and increasing. Do you see that? So it is gradient is positive and increasing. Also, we have this particular portion where the graph is concave up. So in this case, gradient is negative and increasing. So what do you infer? We infer that for concave up, there is one condition and that is gradient is increasing, right? So gradient is increasing. Now, what is the condition for concave down? So clearly, for concave down, the condition is gradient is decreasing. So if you need to figure out the area where on the curve the gradient is positive or increasing, negative or increasing, that means the gradient is increasing. It is always concave up portion. If you want to find where is the gradient decreasing, in that case, it is the area where the gradient is decreasing, right? So it is not negative or positive. It could be both negative or positive, but it should be decreasing. This is kind of very important, right? Now let's move on and see what happens for maximum and minimum points. Question number 4 is identify the points on the graph of f of x where gradient is maximum, minimum, or 0. So we have learned one thing, that the gradient is 0 at turning points, right? So here on the graph, you need to find out where is the gradient maximum, where is the gradient minimum, and where is the gradient 0. So let's begin with 0 first, right? So we know at turning points, gradient is 0, correct? So that is clear. Now, how do we find? So we already know these turning points, and the turning points are C and E, right? So we get our answer, and we can write the 0 as C and E. Now, how do we figure out where is it maximum? So maximum is if we move from A to B, it is increasing, concave up. And the concavity changes, that means it starts decreasing from B to C. So definitely at B, it is maximum, correct? So where the concavity changes, so it is maximum. Where concavity changes from up to down. Now, it's very clear where should it be minimum. So it is going negative, negative, and it is most negative at this point. We're talking about the gradient g, and then it becomes 0 here, right? So from negative to 0, it kind of increases. So it is minimum at d, right? So minimum when concavity changes from down to up. Concave down to concave up. Does make sense? So that is the point D for us. And that should help you to understand all these values. Perfect. So have a good look at the graph, try to visualize it, capture the information for all times to come. If you do that, you're going to save a lot of time in multiple choice questions and also in regular examination. Question number 5 here is explain the conditions when the gradient will not exist. Provide examples. Now that's a very interesting question. I'd like you to pause the video and figure out the conditions where the gradient may not exist. So let's look into a few cases. So what I will do here is I'll draw a few graphs, and those graphs will help you to visualize, and then it'll be very easy for you to answer such questions, correct? Now we have seen absolute function, for example. So it is kind of like this, right? So we have a corner here. At this corner, gradient is not defined. You see, at this corner, if you look from the left side, here the gradient g is less than 0. And at this point, the gradient g is greater than 0. So at this point, here it is not divine. We are not very sure what it is, so we say g does not exist. We'll write d and e for does not exist at corner, right? So which happens to be at x equals to 0 in this particular diagram. Perfect. Now we could also have a situation where the graph could be kind of like this. We call this as a cusp, right? So this is called a cusp. And here also we have similar situation. So we have g does not exist at a cusp. We have seen the graphs of functions which are kind of like this. As you can see, we have a vertical asymptote. So if you have a vertical asymptote, in that case, there is the gradient does not exist. So g does not exist. So a reciprocal function will have a situation kind of like this, right? We have also seen some cases where the graph could be like a step function, right? So if we have a step function, let's say something like this, and this particular also, let's write down the step function. So at this point, since there is a discontinuity, it does not exist. Is that clear to you, right? Now, there could be more situations which are very similar to this. We could also have something like this. Let's say, let me redo this in a way. Let's say we have something like this. We have a hole here, and then the function is increasing. So it will not also exist at a hole. Correct? So these are the points where the gradient will not exist. Now there are some other points also which are very important to understand, and let me make a note of those, and those endpoints of the graph, right? Especially when we are saying that the x value is between a and b, let's say it could be including a and b, then the gradient g does not exist at a and b. So reason being that you cannot find the gradient from both the sides at the end, right? So at the corners, it does not exist, and even at the points, which are the end points of the graph, it will not exist, right? So we'll take up some examples to illustrate that later when we check limits. Question number 6 here is a critical point on the graph of a function. That is what we are going to understand now. Question number 6 is identify the true statement about maximum C and the minimum E. Now this point C is called the maximum value, right? As we have seen, E is the minimum value. When we have periodic functions, in that case, we also use the word crust and trough, right? So these are also the words used for maximum and minimum. But most of the time, when we have a periodic function, we use these terms. Otherwise, we'll stick to maximum and minimum. Now, the question here is, question number 6 is, identify the true statement about maximum C and minimum E. First, A. Gradient changes from decreasing to increasing at minimum. So gradient changes from decreasing to increasing, that is correct. Gradient changes from increasing to decreasing from at maximum. So from increasing to decreasing, that is also correct, right? So it changes from increasing to decreasing, you have a maximum, that is correct. Gradient is zero. If I draw a slope tangent here, it will have a slope of 0. That is also correct. So we notice that all the three statements mentioned here are true, and therefore the best option is D itself, which is all the above statements are true. Right? So at a point where we have a local maximum or a local minimum, we may have a absolute maximum or a minimum value also, as it is in this particular case. All the conditions will be true, right? So the gradient is 0, and also the concave the gradient changes from increasing to decreasing or decreasing to increasing. Perfect. So these two conditions are met. So here let me write down a note. Two conditions for maximum or minimum. Do you see? Both should be true. Both should be true for the maximum to happen, right? So there are always two conditions, and one of them is that the gradient g equals to 0, and it changes from increasing to decreasing, and that results into maximum. Do you see that? But if it is the other way, it is minimum. So if it is gradient is changing from decreasing to increasing, what we get is minimum. Perfect. So how do we figure this out? First thing is we have to find that the gradient should be 0, and we call this point as a critical point or a critical number. Now when we have a critical point, we could have both. We could have a maximum, we could have a minimum, right? There is a possibility of neither also. Correct? Let me give you an example of neither. If I have a graph which is kind of like this, in that case, you will notice that at this point here, we might have a 0. But this point is neither. It is neither maximum nor minimum. And therefore, we now need the second condition. And the second condition is clearly, if it is maximum, then the g value changes from increasing to decreasing. And if it is minimum, then the g value changes from decreasing to increasing. Correct? So both conditions should be true for identifying a point as maximum or minimum. So remember, these two conditions are there for maximum or minimum. Now let's take up the next question based on this. Question number 7 is, explain the conditions for local maximum or local minimum value of the function. So here you need to summarize our learnings, right? So let's try to understand here the conditions. So first condition is, we'll say condition 1. That is gradient g equals to 0. And then we have a condition 2. The condition 2 is, we have to check how the g changes. We have to see the change in g. Correct? So let me write down the condition here. So if it changes from increasing to decreasing, that means changes from increasing to decreasing. In that case, we have maximum. Perfect. On the other hand, if the change is from decreasing to increasing, that is from decreasing to increasing, in that case we have a minimum. Else, neither. You get the idea, right? So let me just give you a graph which will explain all the three things in one shot, and that is a cubic function. So let me graph a function here which makes sense. So let's say we have a graph which is kind of like this. So there's a turning point, there's another turning point, and here. I made a quadratic function. You get the idea. So at this point, we have a maximum. Do you see that? So A is a maximum for us. You can see that the gradient changes from increasing to decreasing. At B, we have a minimum. As the gradient changes from decreasing to increasing, but at C, it is neither. At C, the gradient G goes to 0, but it goes from increasing to increasing. Do you see that? It doesn't change. Concave up to concave up. Do you see that? It is concave up and then to again concave up. So the gradient doesn't change, and therefore it's neither. So I hope that is absolutely clear. It's a very critical point to understand. So if I say that the gradient is zero, it could be maximum, minimum, or either. So we have to perform the second test, and therefore we have both the conditions to be fulfilled to identify a point as a maximum or a minimum. Perfect. Now that's a very important aspect. Let's look into question number 8, which is sketch graph of the gradient for the following function. So we'll just take a semicircle here. The equation is given to us 25 minus x squared within square root. So that is minus 5 to plus 5 is the domain. Now 25 minus x squared square root is a semicircle. As you can see, the graph is being provided to you. You need to sketch the graph of the gradient function, correct? So we need to sketch the graph of the gradient function. Let this be g. So we'll sketch it right here on the same graph paper. How do we do that? So the approach could be that we could have different approaches, of course, but it is always good to start from the points which are very certain and critical. So first point is the turning point. So look for turning point. So we have a turning point at x equals to 0. And at the turning point, if you draw a tangent line, which is kind of like this, you know it is horizontal, and therefore we know that the gradient is 0. So you can mark the point gradient equals to 0 on the graph itself. So that becomes one of your point for g of x. And the other thing which you could look into is the endpoints. At endpoints, we know that the gradient g does not exist. Now, in this particular case, the endpoints are at plus and minus 5. And we could draw vertical asymptotes at these endpoints, correct? So, which are at x equals to plus and minus 5. As a part on the graph, we could actually show it with vertical asymptotes. Since these are very, very high values, if you try to draw a tangent at these points, when you're approaching from inside out, so if you're approaching from this side, for example, the value is extremely high but negative. And on this side also, the slope becomes extremely high, approaching negative infinity. So that is shown by the vertical asymptote, right? So we have these vertical asymptotes at the point. Now, what you also notice here is that if I draw a tangent line somewhere in the quadrant 1, in that case, the tangent line is negative. Slope is negative, right? So what we notice in that quadrant 1, we have a gradient value, which is negative, right? So we have gradient g, which is negative, less than 0. However, in quadrant 2, we have the gradient value g, which is greater than 0. Since if I draw a tangent line in this particular quadrant, it is rising. Do you see that? So it is falling and rising. And therefore, we have an idea that it is 0 in the center, rising and falling. Perfect. Now, we can look for the tangent, and it's a semicircle. So it's a good idea to identify some other points which are easy to work with. So if I go through these corners, then we know this line is y equals to x. Slope is 1, and therefore the slope of the tangent will also be 1. And this particular point will give a value of 1, which corresponds to right there. But since it is negative 1. So I should have drawn here, right? So right there. So this point is where we're looking for negative 1 value. Similarly, on this side, if I go with this y equals to x, it hits at this particular point, and so there it will have a positive 1 value. Now, we have three critical points here, and fourth and fifth are the boundary conditions. So based on this, we could actually sketch the graph. And let me sketch the graph based on the information we have here, which is fairly accurate. So it can go like this, and there you go. So that becomes the graph of the gradient function. Do you see that? So that becomes the graph of gradient function. So this is graph of, is that clear to you, right? So those are the typical points for which we actually found them using the slope of y equals to x and y equals to minus x. You get an idea, right? So in quadrant 1, we could draw a line y equals to x, find the point of intersection. Here we could draw a line y equals to minus x, find the point of intersection, and we know that this is gradient with a negative 1, and that is gradient with positive 1. And now we have three critical points, and with that, and the vertical asymptotes on the side, we could draw the gradient of this particular function. Is that clear to you? Perfect. Have a good look at it and understand the concept. Now, let's take up the next question, which is we're trying to relate now the graph of displacement, velocity, and acceleration. So, question number 9 is graph of displacement, velocity, and acceleration are given below. Identify them and providing support to your answer. So you need to provide support to your answer. Identify which graph represents displacement, which graph represents velocity, and which graph represents acceleration. So we have three graphs, one in color red, the other one in blue, and a straight line in green. Take your time to answer this particular question. So we know one thing, that is, we can write that velocity is rate of change of displacement, correct? And we also know that acceleration is rate of change of velocity. That should help you to figure it out. Now, how do we connect the graph? So I will suggest that the best thing to look into is turning point. So to begin with, we'll start with the turning point itself, and we'll say, well, look at turning points. Right? So the turning point, let's say we are looking at this particular turning point and the graph of this cubic function, then we are looking for a turning point. So the gradient g equals to 0. Then see which one corresponds to that. And clearly we got our answer. If this is there, then we have a hit on the blue graph. So that clearly indicates that blue graph is gradient of the red one. Correct? Similarly, if I look at the other turning point, then also we get a corresponding 0 on the blue graph, correct? So we see from here that we got one relation, and that is that the parabola which is in blue is gradient of cubic function, which is in red. Is that clear? So how did we connect it? We connected simply because of those turning points. Makes sense. You could also see increasing and decreasing behavior to ensure that your answer is correct. Perfect. So you can see from here that the graph has an increasing from 0 to the turning point, and that corresponds to positive value for the blue line. Do you see that? And after that, the red line is going downwards, decreasing, negative slope, and we have this portion of the blue which is negative. Thereafter, after the turning point, gradient is increasing, and we have a positive corresponding value on the parabola. So they connect. Perfect. Now let's look into the blue graph, which is parabola. Start with the turning point. Clearly, this turning point corresponds to a zero on a straight line. So we get that the straight line, which is b of x, is gradient of the parabola, which is a of x, right? So now we have our answers. So the displacement function is the one which is in red, right? So we know that c of x is displacement. The acceleration is rather, well, let's go to velocity, which is in blue, which is b of x, and correct. So no, a of x is blue. This is a here, right? So this is blue. Okay. So the answer here is E. B of x is a straight line, which is the gradient of the velocity. This makes sense to you. Have a good look at this graph. It really helps. So what we observe here is that for polynomial functions, it is a very easy pick. You know that the degree decreases with each gradient. So the displacement is cubic function here with degree 3. Velocity, which is gradient of displacement, is the quadratic function with degree 2. Acceleration, which is gradient of velocity, is a straight line with degree 1. Perfect. But now, when we get into the complicated graphs which are not polynomials, it could be very difficult to find the answer. So let's take one, which is question number 10 for us. Now, those are the questions which are expected in the examination, and they could be very difficult. So question number 10 here is, graph of displacement, velocity, and acceleration are given below. Associate the correct order for displacement, velocity, and acceleration. The three graphs are shown, one in black, then blue, and then green. So you can pause the video and answer this particular question. Well, our approach should be exactly same as we did for the polynomials. So we'll begin with the turning points, just as we did earlier. So the very first turning point is what? So we have to look for turning points. So let me add TP for turning points. So here we have a turning point in graph of A. Now this turning point corresponds to a 0, right? So there is only one graph which is corresponding to 0. So we can say that B of x is gradient of A of x. Does make sense to you, right? So you're looking at the turning point and associating the derivative. Now let's look into B of x and see if this method really works. Okay, so let's look into B of x. I'm using another ink now. So in this graph of B of x, we have a turning point here. And we see that this corresponds to a 0. And we do have a turning point here, which also corresponds to a 0. So since these corresponds, we see that the last graph, which is C of x, is derivative of B of x. Or we can say C of x is gradient of B of x. All right? So we have, in a very short period of time, figured out what is displacement, what is velocity, and what is acceleration from the given graph. Does make sense to you, right? So the displacement is the function a of x and then b of x and c of x. So the answer E is perfectly right. Is that clear to you? That is how we are going to answer complicated questions. Just one point can help us identify. You can always look into other features while confirming your answer. For example, a of x. Now, if you look at a of x, this portion is positive gradient, correct? g is greater than 0. And you can clearly see that the portion of the graph here is positive. And in this portion, g is less than 0, and the graph here is negative. Do you see that portion? So here it is negative. Right. So we have b of x is basically less than 0. It makes sense. So now we confirm that these graphs are related as a gradient of one another, right? So that is how you could confirm, but their turning point is a very critical point to match the graphs. So let me write down a note here, and that is match turning point with 0 on gradient. That is key. So if you do that, you are in a good position to identify which graph may represent the gradient of the other. Perfect. With that, we come to an end of this particular session. So I hope you find it interesting and useful. We covered all these topics, and our focus was to visualize and then find the solutions, and that really helps. So remember, the main idea of this particular thing was to visualize and remember and recall. So if you really look at these graphs, the gradients and their relation, the concavity, the turning points, you can actually uh, do fairly well when it comes to rate of change or gradients or slopes. I hope that makes sense. Feel free to write a comment, share your views, and if you like and subscribe to my videos, that'd be great. Thanks for your time and all the best.